right, welcome back. We're on topic 4.5. We're talking about local linearity or linearization. Basically, that means if we zoom in, really zoom in to a specific point on a graph, we can approximate that it's a linear function. And that's to help talk about the behavior and to approximate values of that function. So we're going to look at Desmos for a second. We're going to look at this graph x squared here. We all know x squared. So if we zoom in to any point, let's say 1, 1, see if I can get this zoomed in there, right? And you can see if I keep zooming in on this point 1, 1, could zoom in even more if I wanted to. You get to the point where you can approximate that it's a linear function, right? Which is going to help us find values on it, right? So we're using this linear function to approximate values of functions that are not lines. You can do this for any function. So let's turn on absolute value of x minus 1. I'll zoom back out. Now let's zoom in on a point, let's say 1. Let's zoom in on, well, this is a linear function, right? On the two sides. But what happens if we zoom in here at this vertex 1, 0? Keep zooming in, right? Here, we can also approximate that it's approximate. I'm saying that word wrong. We can approximate this as a linear function, right? But because it is on both sides. I'm going to zoom in at, I feel like that's not the best example to start with. We'll come back to that one. I'm going to go to this root of 4 minus x squared, this green function, if I could zoom out, right? So it's semicircle. And you could see, right, if I zoom in on any point, so if I zoom in here at 2, 0, it's going to eventually look like a horizontal line. If I keep zooming in on any other point and you get close enough, you can approximate it as a line, right? You're just narrowing your interval, zooming in so that it's linear. You can do that with this purple one, x to the 1,000th as well, right? Even at these corners, when you get in there, these corners aren't really, it's not even really a corner, right? It looks like one, but when you get in there, you can approximate that close enough. I keep zooming in that it will be just a line, right? So we're going to do this with some functions today. So I'm going to switch over to the notes. And we're going to start with this first example, which we're going to approximate the value of root x when x equals 4.36. So if I come back, I'm just going to type, we're going to go back to Desmos and type root x. Turn that on. Let's find it. And we are supposed to approximate the value at 4.36, right? So somewhere, keep zooming out, somewhere here, right? And if we had Desmos, you can actually find the value. But let's say you didn't. How can you approximate it using a linear function? Okay. Well, first thing, because we're talking about the square root of x, and x is 4.36, one thing that I know is that x is more than 2, right? It's a bit more than 2. Okay, so we know, and I'm going to write that f of x is equal to root x, which is equal to x to the 1/2. So if we find the derivative, f prime of x, that will be equal to 1/2 times x to the negative 1/2, right? It's one we've done many times. So we can, we're going to find the closest one we could actually do without a calculator, right? So what we can find is f prime of 4. So what is the slope of the tangent line at 4? Well, if I plug 4 in, I would end up with 1/2 times x to the negative 1/2, 4 to the negative 1/2, which leaves us with 1/4. Okay, so we know that the slope of the tangent line when x equals 4 is 1/4. Okay, so we are going to, let me draw a sketch over here. There's our graph from Desmos. Oh, I realized on Desmos I didn't put root x, I had x root x, right? So remember the graph looks like this. I didn't even pay attention. So when I come back here, and I can approximate the graph looks something like that, right? So let's say here's 4. What we're going to do is we are going to approximate that this function is a line right here, right? Because we've zoomed in so much that we're just taking that portion of the function where it's a line, and we're going to use that to figure out the value of the function at 4.36. So we're taking this tangent line and approximating it as the function at that point around 4. So what we're going to do is we're going to find the linearization. So what we're going to call this L of x. I'm going to assume this is a linear function, right? And it's going to be equal to the value of the function at 4, right? Because that's where it starts, right here. We know it intersects there, this tangent line. And then we're going to add the change in y, right? So that little change from here to wherever it's 4.36. Sorry, that's so sloppy. So how do we do that? So now I'm going to just use this text box. So L of x, the linearization that we're going to approximate of, now we're going to actually find it at 4.36, right, is going to be equal, well, what's the value of f of 4? We know it's 1/4. No, it's not 1/4. I don't know why I said that. It's 2. I'm just going to type this. And I'll type change in y because I can't find the triangle. So let's type this in. 4.36 equals f of 4 is 2, right? And now what is that change in y? Well, that change in y is going to be equal to the slope of the line, so 1/4, times the change in x, so the difference from 4 to 4.36 and 4. So 4.36 minus 4, right? That is the change in y, the slope times the distance in x. So then we can solve that, and we would end up with 2 plus 1/4 times 0.36, which ends up being about, say, approximately 2, and I have it in a fraction here. I don't know why we're in a fraction. Let's see what that is in a decimal. 1 divided by 4 times 0.36 plus 2. You end up with 2.09. Okay, so we're, by taking this tangent line and approximating it as the function for that small window between 4 and 4.36, we can say that the value of the function when x is equal to 4.36 is around 2.09. And let's go back and see, is that true? So I'm going to try to see if I can get to 4.36. Oh, there we are. So the actual value is, it's just there, around 2.088. I think I had it a second ago, right? So something in there. So you can see 2.09 is a pretty good estimate. And we were able to do that by using this tangent line and approximating it as the function for that small window. Okay, so let's do this again. Let's try another one. Find the linear approximation of f around x equals -1. So let's find the equation of the tangent line for this function. So let me get my. So let's find f prime of x. Let's find the slope of that tangent line at that point. So f prime of x is going to be equal to, I think I'm going to just have to write it because we're going to have to use, we can rewrite this as x minus 1 to the -1, right? And then just use the chain rule. So that you end up with, let me finish that off. You end up with f prime of x is equal to negative x minus 1 all raised to the -2 times the derivative of the inner function is just 1, right? The derivative of x, just using chain rule. So if I need to find the slope at 1, let's plug in 1. F prime of 1 equals the negative of 1 minus 1 times -2. Or to raise the -2 power, I'm just going to ignore that. This ends up being the negative of, oh, this is -1. Hopefully you caught that. It should be a negative on f prime of -1. So that ends up being a negative of -2 all raised to the -2 power. So you end up with -1/4. So the slope of that tangent line at x equals -1 is -1/4. So all we need to do is write an equation of the line, right, for this linearization. Let's write an equation of the line. And hopefully you guys saw that this y value is saying take the initial value and add the change in y, which is really what point slope is doing with some things distributed. So let's just write it in point slope first. Maybe that this way will make a little bit more sense to you guys. So remember, point slope is y minus y1 equals m times x minus x1. So it's going to be y plus, well, what is the y value if I plug in -1? So that would be 1 over -1 minus 1. That would be -1/2. So that's y plus 1/2 equals the slope, which is 1/4, -1/4, times x minus, and the x1 is -1, so that's +1. So there's my point slope form, right? So this is the equation of the line that we can use. This is the linear approximation to find the value of f around the point -1. So the last thing you would have to do to really set it up would just be to solve for y, right? So y equals -1/4 times x plus 1 all minus 1/2. Now I can use that to approximate the value of the function around -1, right? We're assuming it's a line there. Let's try another one. All right, so here's where we formalize the definition. And this is kind of what I use in this first example, but this is how, this is what you could write as your linear approximation, your formula for it. So the linear approximation, L of x, applies to a differentiable function at a given point by simply doing this. L of x equals the initial y value plus the change in y, right? Which is the derivative, the slope, times the change in x. The closer the value you're looking for is to that initial point, the better approximation it is. So for example, here 4.36 was pretty close to 4. So it worked out. But if we got even, the closer we get to 4, the better our linear approximation is, right? Because we're zooming in closer and closer. So let's try this one. It says to find the linear approximation to the function sine of x near x equals 0. And then once we find the linear approximation, they want us to use it to approximate the value of sine of 0.1. So I know I need to get all this stuff right here for L of x. So the first thing I'm going to do is just find f prime of x. So f prime of x. And what's the derivative of sine of x? Well, that's just cosine of x. Okay, so then we need, let's write everything down. Let's do this. So L of x is going to be equal to, well, the value of the function at the initial point. So sine of, what are they telling us the point is? X sub naught is 0. Plus the derivative evaluated at 0. So cosine of 0. That's the slope, right? Times the change in x. So what is the change in x? The change in x is going to be, I'm just going to write that right now, minus 0. So now we can actually find this, and I'm not, I think it'll be better, for the value they gave us, 0.1. So this is our linear approximation for 0.1. Sine of 0 plus cosine of 0 times, well, what is our x they've given us? 0.1 take away 0. 1, 0. So then we're just going to solve all that. Sine of 0 comes out to be, I'll write it underneath. So L of 0.1. Sine of 0 is, just putting that period in there, 0. Plus, what's cosine of 0? 1. Times, what's the difference of 0.1 minus 0? 0.1. And then when we solve all that, you end up with 0.1, right? So our linear approximation is this right here, what I wrote in red. And we've used that to evaluate the function at 0.1, and we think it's around 0.1. So let's come to Desmos and check. Let's type in sine of x. How close was our approximation? So let's zoom into 0.1. When x is 0.1, I think I need to zoom in a little bit more. Let's come over here. So when x is 0.1, you can see the value of y is also around 0.1. Can't get there. Oh, so 0.0998. So how close were we? Let's go back. The actual value was 0.998. So we were really, really close, right? Why? Because 0.1 is pretty close to 0. All right. Now let's keep going through this. So one thing to note, though, is when you're using a linear approximation. So if I go back here, we use the tangent line to approximate this value as a linear function at 0.1. So the tangent line here would be going above the actual function. So it's an overestimate, right? So that's why our value was a little bit larger than the actual value. So you have to always think, if I'm using that tangent line as an approximation, am I overestimating or underestimating? Okay. So let's come back and try a few more. If you want to pause and do these on your own and then come back and check, you can. So for each problem, find the linear approximation L of x at f to f at x sub 0. Graph f and L. So we're not going to graph. We're just going to solve these. So this is f of x. Okay, so the first thing we want to do is to find the slope, find the derivative. So let's find f prime of x. And when I worked that out, I ended up with 5 times x plus 1 to the 4th. And then the derivative of the inner function is just times 1, so we don't have to worry about it. So let's evaluate that at 2, because they're saying that f or x sub naught is 2. So when you plug in 2, you end up with 405, right? 2 plus 1 is 3. 3 to the 4th power times 5, you get 405. So now we're going to actually find the value of the function at 2. We need that too, right? Or where we're starting off. And when you plug in 2, you end up with 3 to the 5th, which comes out to 243. So now let's do our linear approximation. So we know that L of x is equal to what? It's equal to 243. Yeah, it's equal to 2. Well, I'm going to write 2 here. L of 2 is equal to 243 plus what? Well, the slope is 405. And then our x minus our x sub naught is 2. Okay. All right, let's try another one. So we know we need the slope. So what's f prime of x? F prime of x here is 3x squared. Take away 0, so I don't need that. They're telling us x sub naught is 0, so f prime of 0, when I plug in 0, is just 0. And I need the value of the function at 0. When I plug in that, it's 0 cubed minus 1, it's minus 1. And now I'm going to use all that for my linear approximation, right? So L, and I'm realizing I made a mistake in this one. It shouldn't be L of 2, it's just L of x, right? You're using this to find, approximate any value of x using 2. But the closer you are to 2, the better it is. So here, L of x is going to equal to, what's our initial value? We're starting at -1. That's our f sub 0, and we're adding the slope, which is 0. And then we are taking x minus 0. Then we can simplify that to L of x equals -1, right? So y here always equals -1. So why is that? Let's come back. I'm going to type in, go to Desmos real quick. So this is saying if we're approximating around 0, so let's come back. If we're approximating around 0, the value is always, what did we say? -1. And then we can see that that's really not a good approximation. Well, why is that not a good approximation here? Because this is, there's no slope here around 0. So while we approximated it using this linear function, it is not the best approximation. So you've got to be thinking about that. So hopefully what I want you guys to see out of this is all you're doing for linear approximation is taking the equation of the tangent line and using it to approximate that function in this very small zoomed in window. Okay, so you can use it to find values. Let's try one more. Okay, here is f of x. So let's find f prime of x. That's going to be equal to 2/3 times x raised to the 2/3 minus 1 is minus 1/3. Right? And then let's evaluate at the point they gave us, which is 1. That leaves us 1 to the negative 1/3 times 2/3 is just 2/3. Okay, now let's evaluate the actual function at 1. Well, 1 to the 2/3 is just 1. So now when we write our linear approximation, L of x is equal to our starting point, which is 1, plus our change in x. Well, our slope here is 2/3, and then it's x minus 1. Okay, so we can use this to approximate the value of a function around x equals 1. And I'm just going to come over back to this one, and let's check x equals 2/3. That's what the function looks like. And we were approximating around x equals 1. So what I can see here is that this function is curving down a little bit. So at 1, my tangent line is actually above it. So I know my tangent line is going to, when I use that, is an overestimate of the values around 1. So keeping that in mind, because a lot of times when you see these questions, it will ask you to find the linearization or approximate it, and then also decide if it's an over or an underestimate. Okay, so always keep that in mind. Signing off. See you next time.